In the 1947 National Electrical Code, grounding and bonding of electrical systems resided in Article 250, just as it does today. However, the 1947 version of Article 250 was considerably shorter and less organized than its current counterpart. Section 250.61 in the 1947 NEC addressed the utilization of the grounded circuit conductor for equipment grounding purposes. The textual content of Section 250.61 in the 1947 NEC is verbatim to the text found in Section 250.61 in the 1993 NEC. However, a pivotal shift occurred in the NEC in 1959. A new section, designated as Section 250.52, was incorporated into Article 250. This section mandated that the equipment grounding conductor be routed alongside the circuit conductors, a requirement absent in the 1947 NEC. Prior to the 1959 NEC, it was standard practice to run the equipment grounding conductor independently of the circuit conductors. This practice was frequently employed in subpanels, where the equipment grounding conductor shared the same raceway as the neutral conductor. This approach was deemed acceptable due to the neutral conductor being grounded at the service entrance, thereby allowing it to serve as an equipment grounding conductor. Nevertheless, the 1959 NEC requirement stipulating that the equipment grounding conductor be run with the circuit conductors effectively prohibited the utilization of the neutral conductor as an equipment grounding conductor. This prohibition stemmed from the requirement for the equipment grounding conductor be routed within the same raceway as the circuit conductors, while the neutral conductor does not qualify as a circuit conductor. Consequently, the 1959 NEC requirement necessitated the installation of a separate equipment grounding conductor to subpanels. This practice has remained a consistent requirement in subsequent editions of the NEC, including the 2005 edition. Therefore, to address the inquiry, it is not uncommon to encounter older subpanels lacking ground-neutral separation. This prevalence arises from the fact that the NEC did not mandate ground-neutral separation in subpanels until the 1959 edition. The evolution of electrical codes reflects an ongoing effort to enhance safety and minimize potential hazards. The shift in grounding practices, particularly concerning ground-neutral separation in subpanels, highlights this evolution. Understanding the historical context behind these changes is crucial for electrical professionals and anyone involved in maintaining or upgrading electrical systems. The rationale behind requiring a separate equipment grounding conductor is rooted in the principles of electrical safety and fault current management. When a fault occurs in an electrical system, such as a short circuit or a ground fault, a path for the fault current to return to the source is essential. This path allows the overcurrent protective devices, like circuit breakers or fuses, to operate and de-energize the circuit, preventing potential hazards like electrical shock or fire. Prior to the 1959 NEC, relying on the neutral conductor as an equipment grounding conductor presented certain limitations. While the neutral conductor is grounded at the service entrance, using it for equipment grounding in subpanels can create a scenario where fault current flows through the neutral conductor. This can lead to voltage drops and potentially create a difference in potential between the neutral conductor and grounded metal parts, increasing the risk of electric shock. By requiring a separate equipment grounding conductor, the 1959 NEC provided a dedicated, low-impedance path for fault current to return to the source. This separate path minimizes the flow of fault current through the neutral conductor, reducing voltage drops and potential differences. The equipment grounding conductor is typically bonded to the metal enclosures of electrical equipment and connected back to the grounding electrode system at the service entrance. This creates a robust and reliable grounding system that enhances safety. The 1959 NEC change also addressed concerns related to induced current and electromagnetic interference. When fault current flows through the neutral conductor, it can induce currents in nearby metal objects, potentially causing them to become energized. A separate equipment grounding conductor minimizes this effect by providing a more direct path for fault current, reducing the likelihood of induced currents. The evolution of electrical codes is a continuous process driven by technological advancements, research, and practical experience. The change in grounding practices in the 1959 NEC is just one example of how electrical codes adapt to improve safety and performance. Understanding the historical context behind these changes is essential for electrical professionals to make informed decisions and ensure compliance with current codes. The specific requirements for grounding and bonding can vary depending on the jurisdiction and the edition of the NEC in effect. It is crucial to consult the latest edition of the NEC and any local amendments to ensure that electrical installations meet the applicable standards. The NEC provides detailed guidelines for grounding and bonding, covering topics such as the size and type of grounding conductors, the methods for connecting grounding conductors to equipment, and the requirements for grounding electrode systems. Adhering to these guidelines is essential for creating a safe and reliable electrical system. In addition to the NEC, other standards and best practices can provide valuable guidance on grounding and bonding. These resources can help electrical professionals stay up to date on the latest technologies and techniques and ensure that the electrical installations meet the highest standards of safety and performance. The concept of ground-neutral separation is closely related to the broader topic of electrical safety. Electricity is a powerful force that can be dangerous if not handled properly. Grounding and bonding are essential components of an electrical safety system, providing a path for fault current to flow and minimizing the risk of electric shock. Other important aspects of electrical safety include proper insulation, overcurrent protection, and the use of ground fault circuit interrupters, or GFCIs. GFCIs are devices that monitor the current flowing in a circuit and quickly to energize the circuit if a ground fault is detected. GFCIs are commonly used in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. Regular inspection and maintenance of electrical systems are also crucial for ensuring safety. Electrical systems should be inspected periodically to identify any potential hazards, such as loose connections, damaged wiring, or overloaded circuits. Any identified hazards should be corrected promptly to prevent accidents. Electrical safety is a shared responsibility. Electrical professionals, homeowners, and anyone who works with electricity should be aware of the potential hazards and take precautions to minimize the risk of accidents. By following the NEC and other applicable standards, using proper techniques, and maintaining electrical systems regularly, we can create a safer environment for everyone. The information presented here is intended for general educational purposes only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrical professional before performing any electrical work. Electrical work can be dangerous, and it is essential to have the necessary knowledge, skills, and equipment to perform it safely. The evolution of electrical codes is driven by a combination of factors, including technological advancements, safety concerns, and the accumulation of practical experience. As new technologies emerge and our understanding of electrical phenomena deepens, electrical codes are updated to reflect the latest knowledge and best practices. Safety concerns are a primary driver of code changes. When accidents or incidents occur, they are often investigated to determine the root causes. If the investigation reveals that the existing codes were inadequate or that a particular practice was unsafe, the codes are revised to address the identified issues. The accumulation of practical experience also plays a significant role in code development. Electrical professionals who work in the field on a daily basis often have valuable insights into the effectiveness of different practices and the potential for improvement. Their feedback is considered during the code revision process, helping to ensure that the codes are practical and relevant. The process of developing and revising electrical codes is typically a collaborative effort involving a wide range of stakeholders, including electrical engineers, contractors, inspectors, manufacturers, and consumer representatives. These stakeholders work together to identify potential issues, propose solutions, and develop consensus-based codes that reflect the best interests of the electrical industry and the public. The National Electrical Code, or NEC, is the most widely adopted electrical code in the United States. It is developed and maintained by the National Fire Protection Association, or NFPA, a non-profit organization that develops and publishes codes and standards related to fire safety and other hazards. The NEC is updated every 3 years, and each edition reflects the latest advancements in electrical technology and safety practices. The NEC is organized into chapters, articles, and sections covering a wide range of topics related to electrical installations. It provides detailed requirements for wiring methods, overcurrent protection, grounding and bonding, equipment installation, and other aspects of electrical systems. The NEC is a comprehensive and complex document, and it is essential for electrical professionals to have a thorough understanding of its provisions. In addition to the NEC, other codes and standards may apply to electrical installations depending on the jurisdiction and the type of installation. These codes and standards may address specific topics such as energy efficiency, accessibility, or fire safety. It is important to be aware of all applicable codes and standards and to ensure that electrical installations comply with their requirements. Continuing education is essential for electrical professionals to stay up to date on the latest codes, standards, and technologies. The electrical industry is constantly evolving, and it is important to have the knowledge and skills necessary to perform electrical work safely and effectively. Continuing education courses are offered by a variety of organizations, including trade associations, colleges, and universities. These courses cover a wide range of topics, from basic electrical theory to advanced topics such as power quality and renewable energy. By participating in continuing education, electrical professionals can enhance their knowledge, improve their skills, and advance their careers. The information presented here is intended for general educational purposes only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrical professional before performing any electrical work. Electrical work can be dangerous, and it is essential to have the necessary knowledge, skills, and equipment to perform it safely. When dealing with electrical systems, safety should always be the top priority. Electricity can be dangerous, and even a small mistake can have serious consequences. Before working on any electrical system, it is essential to take the necessary precautions to protect yourself from electric shock and other hazards. Firstly, always to energize the circuit before working on it. This means turning off the circuit breaker or removing the fuse that supplies power to the circuit. Use a voltage tester to verify that the circuit is de-energized before touching any wires or components. Secondly, wear appropriate personal protective equipment, or PPE. This may include safety glasses, gloves, and insulated tools. Safety glasses will protect your eyes from flying debris, gloves will protect your hands from electric shock, and insulated tools will prevent you from accidentally creating a short circuit. Thirdly, work in a well-lit area. This will help you see what you are doing and avoid making mistakes. If necessary, use a flashlight or other portable light source to illuminate the work area. Fourthly, keep the work area clean and organized. This will help you avoid tripping over tools or materials and prevent accidents. Fifthly, if you are not comfortable working on an electrical system, do not attempt it. Call a qualified electrical professional to perform the work. Electrical work can be dangerous, and it is essential to have the necessary knowledge, skills, and equipment to perform it safely. In addition to these basic safety precautions, there are other things you can do to minimize the risk of accidents when working with electricity. These include using proper wiring methods, ensuring that all electrical connections are tight and secure, and following the manufacturer's instructions for installing electrical equipment. It is also important to be aware of the potential hazards associated with different types of electrical equipment. For example, power tools can be dangerous if not used properly. Always read and follow the manufacturer's instructions for using power tools, and wear appropriate PPE. Extension cords can also be a fire hazard if not used properly. Do not overload extension cords and do not run them under rugs or carpets. If you are using an extension cord outdoors, make sure it is rated for outdoor use. By following these safety precautions, you can minimize the risk of accidents when working with electricity and protect yourself from electric shock and other hazards. The information presented here is intended for general educational purposes only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrical professional before performing any electrical work. Electrical codes are constantly evolving to address new technologies and improve safety. Staying up to date on the latest code changes is essential for electrical professionals to ensure that their work complies with current standards. The National Electrical Code, or NEC, is updated every 3 years, and each edition reflects the latest advancements in electrical technology and safety practices. The NEC is a comprehensive and complex document, and it is essential for electrical professionals to have a thorough understanding of its provisions. Changes to the NEC can have a significant impact on electrical installations. For example, a change in the requirements for grounding and bonding can require changes to the way electrical systems are installed. A change in the requirements for overcurrent protection can require the use of different types of circuit breakers or fuses. To stay up to date on the latest code changes, electrical professionals should attend continuing education courses, read industry publications, and consult with other experts in the field. They should also participate in the code development process by providing feedback on proposed code changes. The code development process is a collaborative effort involving a wide range of stakeholders, including electrical engineers, contractors, inspectors, manufacturers, and consumer representatives. These stakeholders work together to identify potential issues, propose solutions, and develop consensus-based codes that reflect the best interests of the electrical industry and the public. By staying up to date on the latest code changes and participating in the code development process, electrical professionals can help ensure that electrical installations are safe, reliable, and compliant with current standards. The information presented here is intended for general educational purposes only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrical professional before performing any electrical work. Electrical systems are complex and require careful design, installation, and maintenance. Proper grounding and bonding are essential for ensuring the safety and reliability of electrical systems. Grounding provides a path for fault current to flow back to the source, allowing overcurrent protective devices to operate and to energize the circuit. Bonding connects metal parts of an electrical system together, creating a low impedance path for fault current to flow. Without proper grounding and bonding, fault current can flow through unintended paths such as the human body, causing electric shock. Grounding and bonding also help to reduce electromagnetic interference, or EMI, which can disrupt the operation of electronic equipment. The NEC provides detailed requirements for grounding and bonding, covering topics such as the size and type of grounding conductors, the methods for connecting grounding conductors to equipment, and the requirements for grounding electrode systems. The NEC also addresses the separation of neutral and grounding conductors in subpanels. As discussed earlier, the NEC requires that neutral and grounding conductors be separated in subpanels to prevent fault current from flowing through the neutral conductor. This helps to reduce voltage drops and potential differences, minimizing the risk of electric shock. The specific requirements for grounding and bonding can vary depending on the type of electrical system and the application. It is important to consult the NEC and other applicable standards to ensure that electrical systems are properly grounded and bonded. Regular inspection and maintenance of electrical systems are also crucial for ensuring that grounding and bonding connections are tight and secure. Loose or corroded connections can increase the impedance of the grounding path, reducing its effectiveness. The information presented here is intended for general educational purposes only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrical professional before performing any electrical work. Electrical safety is a shared responsibility. Electrical professionals, homeowners, and anyone who works with electricity should be aware of the potential hazards and take precautions to minimize the risk of accidents. By following the NEC and other applicable standards, using proper techniques, and maintaining electrical systems regularly, we can create a safer environment for everyone.